So to finish up chapter 18, I just wanted to go over percent dissociation. If you see that in the homework, there's a couple problems I didn't assign them yet, but 18.78 and 7.9 say calculate the percent dissociation. Guys, all percent dissociation is your 5% check. It might be over 5%, but it's the same principle where you take your X that you solved in Icebox and you place it over your original concentration. And that's what we do for the 5% check. Change over initial times 100. And if it's less than 5%, we're okay to make that assumption. Well, that is your percent dissociation. What the 5% check is checking is saying that if your acid dissociates under 5%, it's okay to make this assumption and get rid of this X up here and rewrite it like this. So if you see and they ask for percent dissociation, they're really just asking what's the 5% check value. Okay, so it's nothing new to worry about and say, well, I don't know what the heck they're asking. You've been calculating it the whole time. Now, another thing I want to talk about is buffers. Okay, so if I have water, okay, either way we look at it, I'm going to make two containers of water in here. And if I add acid to the water, okay, if I add acid to the water, I'm going to create hydronium, which is going to cause the pH to drop. Okay. If I add base to water, I'm going to create hydroxide, all right, which is going to cause the pH to go up. What a buffer is a substance that essentially has a resistance to a change in pH with the addition of an acid and a base. So what a buffer contains, usually, is an acid and its conjugate base. Okay, so this is a buffer. So if I add acid, okay, instead of creating the hydronium like I've done up here, the A- comes by and bonds up that acid and essentially keeps it whole. Doesn't allow it to dissociate and bond up to the water to make hydronium. Same thing if I add a base. Instead of the base making hydroxide, the acid essentially reacts with the base and makes water and some salt. Now the thing is, our buffers have a capacity. So there's a point, yes, I could dump this in, the pH won't change. I could dump this in, the pH won't change. But there's a point at which if I keep dumping acid in, acid in, acid in, acid in, acid in, my conjugate base will be gone and used up, and eventually my pH will drop. Now, where this is important is if you're studying, physiological things in a lab, and you need a pH setting. So, like if you're studying, let's say, the human body, and you're studying a specific organ, or if you're just the physiological pH. Our physiological pH is 7.4. We're slightly basic. Now, when we work out and glucose breaks down and we make CO2, large amounts of CO2 can create carbonic acid, which would cause our pH to drop. Well, we have built-in buffer systems. We have a carbonic acid, a protein buffers, we have phosphate buffers, all built in our system so that when we build up that CO2 during the breakdown of glucose, our buffers neutralize it. The issue is if we make too much of it, and we can't stop the making of the CO2, then our buffer system is working, but then gets to capacity, and then our pH could end up dropping. So hyperventilating and hypoventilating. So hyperventilating meaning you're breathing too fast, and hypoventilating meaning you're breathing too slow. If I'm breathing too slow breathing, I could have a drop in my pH because I have too much CO2. I'm not exhaling as fast as I should, so CO2 starts building up in your body, and your buffer starts, when carbonic acid forms, your buffer system neutralizes it, but it becomes overwhelmed and your pH drops. So we call that respiratory acidosis. If I'm breathing too fast, my pH ends up going up because now I'm not keeping enough CO2 in my body. So that's why the myth of breathing into a paper bag if you're hyperventilating has some merit to it. It doesn't work, but you would be exhaling too much CO2, not having enough CO2 in your body. So if you inhale what's in the paper bag, that should just be CO2. But I mean, it's more of a calming mechanism than anything. So we call that respiratory alkalosis. If you're breathing too fast, then your pH ends up going up. All right, so that's why it's important to regulate your breathing, and if you're hypoventilating or hyperventilating, to try to get it back down to normal. Now, we have built-in buffer systems because, hey, when we start burning glucose and it goes through glycolysis and then the citric acid cycle, we're going to produce CO2. I mean, it's the same idea, too. If you have a pond outside or a little koi pond or something like that and there's leaves in it, you want to get all those leaves out as soon as possible because as they break down, they produce CO2, and that could cause a drop in pH in your water basin, essentially. So any of your water systems that are filled with leaves and stuff like that, decaying things, CO2 could build up and drop the pH to an unsafe level. Okay, so we have built-in buffers in our system, and again, if we were studying in a lab setting and we wanted to build a buffer, we would use a conjugate acid or an acid and its conjugate base, or a base and its conjugate acid, and those are what neutralize essentially small changes in pH. So our pH would relatively stay the same until we got through maximum saturation points. Okay, so that's what a buffer is. A buffer is essentially an acid with its conjugate base or a base with its conjugate acid that is going to resist small changes in pH. Now, what we talked about up until this point is if I wanted to change the pH of a solution, I would add an acid and it would drop the pH. I would add a base and it would raise the pH. But salts can also have an effect on the pH of a solution. Okay? So studies have been done, and you can look at them, and environmental studies, for those of you who are interested in environmental science in this area, about salt runoff going into our rivers, lakes, and things like that. And how, much of the runoff affects the pH. So, testing your water in early spring or just after a snowfall or a couple weeks after a snowfall and they've laid salt down, or after a big rain after they've laid salt down, or whatever you want to do, after the first thaw, however you want to look at it, you can watch pH levels change if those salt levels are too high and getting into our water systems. Okay, so salts that, so how can we tell, essentially, if I'm going to raise pH or lower pH? So salts that consist of cations of strong bases and the anions of strong acids have no effect on H plus when they dissolve in water. Okay, so sodium chloride, potassium nitrate. All right, so sodium chloride, sodium hydroxide's the strong base. Hydrochloric acid's the strong acid, so it's a salt between those two, no effect. Potassium hydroxide, strong base. Nitric acid, strong acid, no effect. There you go, ocean acidification. You got it, Kelly. All right, sodium sulfate, sodium perchlorate, so on and so forth. If it's a strong base's cation and a strong acid's anion, not really going to have an effect. So that's why sodium chloride All right, if they're using that as, a laydown or something like that, or the ocean, all right, with sodium chloride in there, not really going to change your pH. But other ions getting into the water system could be change the effect of the pH of the solution and so on. So for any salts whose cation has neutral properties, such as sodium positive or potassium, and whose anions is a conjugate base of a weak acid. Okay, so now we got to go back to our weak acids. We're talking fluorine, okay, cyanide and sulfide, all right, phosphate, and then any of our carbon-based ones, our organic ones. Okay, so if my anion, all right, would make an acid weak, and this is why we went over strong and weak acids. If my anion would make an acid weak, okay, so that's what they mean here when it says whose anion is the conjugate base of a weak acid. So sodium is, a strong base, not relevant. We got fluorine, which is a part of a weak acid. So strong base with a weak acid anion is going to make my solution basic. Okay, so if the anion is a weak acid anion, okay, so if my anion when bonded to hydrogen would give me a weak acid, then I'm going to make my solution basic. So if I were to take the pH of sodium phosphate, it should be basic. Okay. And then a salt whose cation, all right, is the conjugate acid of a weak base, produces an acidic solution. So, remember what makes a strong base. Group 1 and my bigger group 2s. So, lithium, potassium, sodium, calcium, barium, they all make strong bases. If my cation isn't one of those, a group 1 or a bigger group 2, then I'm going to make my solution acidic. So they show you here iron nitrate, aluminum chloride, ammonium chloride. Okay. Things that are not going to be considered strong bases. Ammonium chloride is your exception because ammonium chloride is a weak base when all is said and done. It doesn't follow the strong base rule. Aluminum hydroxide would be not a strong base. Iron hydroxide would not be a strong base. Okay. Or you can look at it as they're saying Fe plus, aluminum, things like that. Those are conjugate acids of our weak bases. So, to review, group 1 metal or large group 2 metal with an anion that would make a strong acid has no effect on the pH of a solution. A group 1 metal or a large group 2 metal, but usually it's a group 1 like they're saying here, sodium or potassium or lithium that has neutral properties, with an anion that would make a weak acid, basic. Anion, weak acid, basic. Cation, that would make a weak base. Okay? Would make my solution acidic. So it says, predict whether aqueous solutions of the following are acidic, basic, or neutral, and write any equation of the ions in water. Okay, so let's take a look here. They give us the answers, all right? But let's look at it. Potassium perchlorate. Potassium would be with hydroxide, would be a strong base. Okay? Chlorate, right here, with a hydrogen to make an acid would be a strong acid. So I've got the cation of a strong base. I've got the anion of a strong acid. Therefore, my solution will be neutral. Okay. Let's look at the next one. Sodium benzoate. I've got sodium. That's from a strong base. But I have this carbon, COO minus. Take that off, and your ion is this right here, which is no different. Well, I mean, it's different, but it's the same idea as acetate. Well, if I put this bonded to, if I put this right here, let me get my little pen here. If I put that right there with a hydrogen, that's going to make a weak acid. So I have a strong base with a weak acid. That should make my solution basic. Let's look at the next one. I've got chromium nitrate. Nitrate with a hydrogen should make a strong acid. Chromium is not a group 1 or large group 2 metal. It's a transition. Therefore, my chromium 3 plus is going to make my solution acidic. Okay. So salts could play a role in changing the pH of a solution. It depends on what your cation and your anion of the salt. All right, questions on that? I'm not worried if you can write out the equation or not. If we had more time and we were sitting in lecture together, then we would work on that a little bit more. But I'll be happy if you could tell me, hey, I look at this salt and it's either going to be neutral, acidic, or basic. Here's a table that sums up these ideas. What if I get a mixture of both? What if I get, like here, under acidic basic? Like this is a weak base and this is a weak acid, weak base. What happens? Well, you could kind of create both. It just depends on what, comparing the Ka to one another. What is ammonium's Ka value versus what is chlorite's Kb value, and compare them, and that would tell you what the pH would be. So if I were looking at, let's say, ammonium chlorite here, okay, so I'm right here in this list. And I want to know, well, I look at it, it doesn't follow any of these rules up here. It's not a group 1 with something that make a strong acid. It's not, something that would make a strong acid and a weak base. It's actually a weak base and a weak acid. Like, what would I do here? Well, what I'd have to do is look up the Ka value of my cation. I'd have to look up my Kb value of my anion and compare them. If the Ka value is greater than the Kb, then I will be an acidic compound. If the Kb is greater than the Ka value, then I'm going to be greater than 7.0, and I'm going to be basic. Okay. If I were to give you those on an exam or something like that, I would have to give you the Kas and Kbs of the, cation and the anion. I'm more going to focus on these right here based on time constraints. Can you look at it and can you tell me whether this will be acidic or basic? Okay. And this table's in your book. It's 18.8. So let's take a look at this. It says, determine whether an aqueous solution of zinc formate is acidic, basic, or neutral. All right. So zinc is not a group 1 or a group 2. Large group 2. It's a transition. It's in 12 or 2B. And this would give me a weak acid if I combine it with hydrogen. So what do we have to do? Well, you have to go and look up what is the Ka and Kb of our zinc and of our HCOO. Well, they tell you that zinc's Ka is 1 times 10 to the negative 9th. Okay. They give us the Ka of HCO minus, which is 1.8, so they have you calculate the Kb. All right, all they're doing here is they're just being smart here. All right, and by smart I mean trying to be wise asses. But what they're doing here is, here's the Ka of zinc. They looked up the Ka of HCOO minus and got this, but I need to compare it as the Kb. So this, they solved and found the Kb. Okay. What they're saying is, hey, if I gave you the Ka, then you should be able to calculate the Kb based on everything we've done up until this point. Well, now to tell whether I'd be acidic or basic, I compare the 1 times 10 to the minus 9th for the zinc and the 5.6 times 10 to the negative 11th for the HCO minus. And since this number is bigger than this number, our solution would be an acidic solution. The Ka is greater than the Kb, so it's acidic. Again, I'm going to focus more on this up here than this down here. But just in case you ever need to calculate it or a bonus question or something pops up. We talked about buffers. Buffers contain conjugate acid-base pairs. Okay, blood buffers, as I mentioned in a previous conversation when we're talking on the board here, our pH is 7.4. If we go above that, 7.8, above 7.8 we could die, below 6.8 we could die. So we need to have built-in buffers. We do. All right, bicarbonate buffers, phosphate, protein buffers. Here's a bicarbonate. All right, what the buffer looks like. Here's your acid. Here's the conjugate base that goes with it. Here's an acid and conjugate base. Okay. All right, we talked about respiratory acidosis and alkalosis. That's all on here. And that essentially ends this chapter. Okay. That ends this chapter, which, ends chapter 18, and we've already done 17. So that's 2 chapters. So we're ready for an exam, is where I'm at. Okay. Now, How is the exam going to be set up? It's going to be just like if you were taking an exam during lecture time. There's going to be problems and all that. The only difference is you're not going to be able to get credit for, partial credit for almost getting it right. But on the other hand, it's going to be multiple choice, so the right answer is right there. You'll have the same amount of time that you would during a regular one of my exams. It's going to be very similar to that. Okay. So what stuff would I look for, or what should I be reviewing? Well, the homework, of course. But, if we had to sum it up, what was going on in the chapters? Okay. Well, if we were summing up what was going on in the chapters, the first thing we talked about was equilibrium. So I would know how to use KC and be able to get KC to KC reverse. All right, and I would know what, KC to the N is. I would know how to do all of that. I'd know how to write my KC expression. Products over reactants. All right, raised to their coefficients. All right, stuff like that. I would know how QC, what's the difference? How does QC relate to KC? Remember, QC is calculated the same way or could be any time during the reaction. What do those values mean? All right. No, you're going to take it during class time, Fiona. So the exam will be able, you'll be able to get into the exam between 9:30, let's say, and 9:50. And as soon as you start it, you'll have 2 hours to take it. I would know Le Chatelier's principle. Yep, I would know that, Tannen. I would know how to do, find the QC. So find QC from, that's all combined there. Find the QC from multiple reactions. And that pretty much does chapter 17. Okay, icebox is in there. But we're also going to use icebox when we talk about acids. So with my acids, I should know how to find a Ka. I should know how to find a Kb. I should know how to find pH. I should know how to find POH. I should know how to find the concentration of OH minus. I should know how to find the concentration of H3O plus. I should know how to do pKa, pKb. I should know about my salts and how they affect pH. I should know about my buffers and what are they. I should know the different definitions of acid and base. I should know what a Lewis acid is or a Lewis base. I should know what Bronsted-Lowry acid base is. I should know what a classical acid base is. I should know what a strong acid is. What's a strong base? All of that. again, if you could do the homework, and I know this looks like a lot of stuff, but it's really not. This is all one problem. All of this right here. QC and KC all based off of this. And then Le Chatelier's principle. Icebox is how you find pH, POH, OH minus, H3O plus, and things like that for weak acids and weak bases. Okay. Now, homework that deals with what we talked about today. Page 837. (18.78 and 7.9). It's Lewis acid stuff. I know I had salt stuff in here somewhere. Yeah. See, they moved buffer stuff into chapter 19. So let me go to the end of chapter 19 here. Let's see what they got here, if there's anything good. Yeah, there's nothing really good there. Just review the definition of a buffer and stuff like that. And we'll get more into it, hopefully, at the end here. Okay. So just look at that and then review the slides on your salts and buffer. Same number of questions that a normal exam is. Maybe a couple more to break it down because I can't do A, B, and C in the multiple choice. So I don't know, 14 questions, something like that. Like for Le Chatelier's principle on a normal exam, I would give you a reaction and say, what would happen if I would do the following, A, B, C, D, and E? Well, I can't do that on a multiple choice exam. So let's say I was going to ask 6 different things there. Like increase the products, decrease the reactants, increase the temperature. If I was going to ask 6 different things there, that would be one question. Well, now I've got to make it into 6 questions. So 20 questions, something like that, but it's really the same length as a regular exam would be. So instead of saying, hey, this Le Chatelier's principle question's worth, 12 points, 2 points for each one, now there's going to be 6 2-point questions asked about that. Something like that.